If you want to know what this here has to do with a powerful product called the exterior product, then stick with me. We will find out how we can encapsulate all important properties of vector subspaces into elements of a new algebra. For example, with this we can see planes and lines and volume elements more through a visual, more through a geometric lens. We treat vector subspaces as elements of our algebra. This algebra is called Geometric Algebra. In this video we will focus on the exterior product that is part of it, but Geometric Algebra is way more powerful and it has also other elements in it. I still try to be formal in the math here, but only as formal as needed to understand what is going on. So let's get started. As promised, we deal with vector subspaces and want to make them elements of our algebra. Let's quickly recap what a vector subspace really is. So we have a tuple consisting of a set V, an addition, plus, and a multiplication. And we say that this is a vector space over the field K. Then U, which is a non-empty set, and a subset of V is a vector subspace of V if for any two vectors U and W that we take out of U, and for any scalar that we take out of the field K, we have those properties. When we add together two vectors, we still reside in U, in the subset. So we say it's closed under addition. And it should also be closed under multiplication with a scalar. So then, with these two properties, U is a vector subspace of V. In this video, we only consider vector subspaces Rn over the field R. So let's focus now on some proper vector subspaces, that is, vector subspaces that contain the origin. For example, we have lines in one dimension, then we have planes in 2 dimensions, and we also have volumes in 3 dimensions. Now we want to extract some kind of structure that describes all of these subspaces. So we need to ask ourselves, what do those spaces have in common? They all span some subspace, they have a weight and an orientation. What do we mean by that? So when I say they span something, well, on the line, you see, we span the line, so we can move a point along the line if we just multiply by a lambda. On the plane, we can do the same with 2 coefficients, and we have our 2 vectors A and B. And for the volume, where we have then 3 vectors and 3 scalars to describe the span of our subspace. They also have a weight. So in this case, for the plane element, this would be its area. For the volume, well, it's volume. And for the line, it could be the speed. Like if you move the point along the line, how quickly do you move it? And then they also have an orientation. For example, for the plane, if we now draw the plane where we first start with the B vector and then the A vector, then we would say that it has opposite direction, like the area element is flipped. For the volume, you know the right-hand rule in physics, so this is the handedness. And then for the line, well, it's the direction in which this vector A points on the line. Now, the really cool thing is that we can actually combine all of these properties into one product, the exterior product, also known as wedge product. For example, consider these 2 planes. On the left side, what you see is a graphical representation of the product A wedge B. But one important property that we want to encode is, like we've seen, the orientation. So on the right side, this is the product of B wedge A, because you start with the vector B and then you go with the vector A to span this whole element. So you see the orientation is different. That's why we want that A wedge B is the negative of B wedge A. And this is called antisymmetry. As a consequence, what happens if we think of the same vector and we take the product? So in this case, we would take A equal to B. Then what follows with this antisymmetry is that this A wedge A is equal to minus A wedge A. And this suggests that A wedge A is 0. So the interpretation here would be that A alone, like the vector A alone, it doesn't span any planar element. So that's why we say, well, it's 0, because the planar element that one vector alone spans, it just has weight 0. It doesn't really exist. Then another important property is scaling. So if you take A wedge beta times B, then this should be the same as if you were to calculate the wedge product A wedge B and then scale this with beta. So to see this visually, let's consider A wedge 2B. So here the beta is 2. Then this should be the same as A wedge B, but this 2 times. This is just all that scaling is saying, really. Now we also want distributivity, like the classic rule, you know, A wedge parentheses B plus C. This should be the same as if we were to factor individually. To get a bit more of a feeling for how this exterior product works, let's take an orthonormal basis consisting of E1 and E2 that spans the subspace A wedge B of R2. So we just write A as a linear combination as we're used to, so we have two coefficients A1 and A2 and multiply them with those basis vectors. Same for B. Now if we expand this and take our properties that we've seen before, in this case distributivity, then what we get is this expression. And as you see here with the discussion we had beforehand, the E1 wedge E1 evaluates to 0. Same for E2 wedge E2. Those two are just 0. They don't span any planar element because it's just one vector. Then with the antisymmetry, we get that E2 wedge E1 is the same as minus E1 wedge E2. So then we can combine those two terms that we have left. So this is just the determinant of this matrix where we write the coefficients of our two vectors A and B in it. As you remember maybe from linear algebra, there you were told that the determinant, well, it gives us the oriented area spanned by A and B relative to the area spanned by the basis vectors E1 and E2. So indeed, here we have encoded in our exterior product an oriented area. And if you write it like this, you even see what the relative geometrical unit is, like E1 wedge E2. To that area element and to that orientation, you compare what your A wedge B is. And this is like nicely encoded in just basically 3 letters, A wedge B. So this is really cool, I think, but so far we cannot write anything beyond A wedge B. For example, you might think that, well, now that we have A wedge B, we can just write A wedge B wedge C to denote the volume element. And we want this to be true, but for this to work, we need one more property, namely associativity. That just means we can place the parentheses wherever we want, such that our expression A wedge B wedge C without parentheses is unambiguous, because it doesn't matter if we first evaluate A wedge B or if we first evaluate B wedge C, it's the same result in the end. This is what associativity is telling us. And to see this visually, think of A wedge B first evaluated. So this would be like the planar element. And then we stack on top along the axis of the vector C those planar elements. And if you do this like infinitesimally small, then you would get the volume. And then this should be the same as if you did B wedge C first, like B wedge C now, as you can see, is another planar element. And then we stack those elements along the direction of A. And then if you know like Levi-Civita, you can even go further and write it like this. B wedge C wedge A, and this should still be the same expression. This is just to see visually what associativity is trying to tell us. Okay, great. So now that we've encoded these properties into the exterior product, we should talk about it a bit more formally in the context of blades and multivectors. What do we have so far? Well, we have a vector A. We can use the wedge product to get a planar element, which we call A wedge B. And then we can even chain this and add more vectors and more vectors. And maybe you don't always want to write this whole expression, so let's give this a name, for example, A. And A is a so-called blade. In this case, we have a 4-blade because we used 4 vectors. In general, the definition of a blade is the exterior product of k vector factors. So in a k-blade A, you just multiply with the exterior product k vectors. So A1 wedge A2 up until AK. And if you think back now, we've already seen a lot of blades. For example, we've seen 1 blade, which is just a vector, a 2-blade, which is A wedge B, this is a bivector. We've seen a 3-blade, a trivector, up until a k-blade. And we also have 0 blades, which are just scalars. At this point, you might be wondering, how do we denote the space that those K blades live in general? And glad that you asked. They live in a linear space of K blades that we denote by this big wedge symbol, then the K as a superscript, like the K, the number of vector factors in a non-zero K blade, and the underlying space Rn. And at this point, you can go more formally in depth about how you construct a space like in a rigorous way with right-sided ideals and so on. But like for this video, this representation is enough. We just need to know how to write down the space. Just think of it as the space reachable by any K blade. In addition, we also have a special symbol called grade. So the grade of a blade is just the number of its vector factors. So for example here, grade of A1 wedge until AK, this just gives us the K. For example, this blade, A wedge B, lives in this linear space of 2 blades. So it has grade 2. And the capital B blade here, it lives in the 3 blade space. So it has grade 3, and the vectors, of course, they always come from the field Rn. And with this, we can also write a bit more formally what the exterior product really is. A mapping between linear spaces of blades. So we multiply 2 blades together of grades K and L respectively and obtain another blade with grade K plus L. So if you take 2 blades, A and B, and you wedge them together to get another blade, then the grade of this blade that you obtain is the sum of the grades of the blades you took beforehand. Okay, well, let's see an example to make this a bit easier. Let's take these 2 blades, capital A and capital B. Now the grade of A is 2 and the grade of B is 3. If you now consider a new blade C that you construct by wedging those 2 blades together, so A wedge B, then as you can see, the grade of C is 5. Like, it's just very natural. But here is a formal way to write it down with the grade. Okay, enough of this. We want to see how we can actually calculate something with it. We have a basis E1, E2, and E3, an orthonormal basis that spans a subspace A wedge B wedge C of R3. Now there's a nice Python library called Clifford from which we import the G3 model, which is like the geometric algebra for R3. And from it, we can access the blades. So G3.blades, and then you write as a key the name of the basis vector. So E1, E2, and E3. And with these basis vectors, we can construct our blades. For example, A as 1 times E1 plus 2 times E2 plus 3 times E3, and B as just some random other blade. Now, as a result, we want to obtain A wedge B. So in this case, let's think this through. If you use the properties that we've already discussed, so distributivity and the antisymmetry, then you will find this expression. To make our syntax a bit more like robust, we will write instead of E1 wedge E2, E1 2, and so on for the other vectors. And then what is really nice, if you just run your Python program, you will find the very same result that we came up with by hand. But like, what? How is this even working? Like, we wrote A wedge B. How can we expect that something like this is just implementing the exterior product? Well, this is done by the Python library that we imported. And to understand it, let's quickly look at what operator overloading means. So if you have a class in Python, for example, my class, with a simple constructor that just stores the value as an instance member of this class, then maybe you want to do something like, well, you instantiate 2 objects, X and Y, and you want to perform an addition, but of course your object is just a custom class, so how could you expect that addition would work? Well, you can't, but what you can do is just implement your own addition. And this is called operator overloading, that you might know from C and C++. And in Python, it's really easy. You just override this special method called add. And in this case, just for fun, let's define it such that it actually subtracts the values from each other. Not the kind of addition you're used to. So you would get 7 plus 3 is 4. But well, we can define it however we want here. And this powerful operator overloading allows us to also override the XOR. Well, the XOR is this little hat that you've seen and that we use now in Python to indicate our exterior product. So now if you wanted, for example, that 7 wedge 3 makes any sense and is equal to 21, then you would just define it like this. This doesn't make any sense, but it's just to show you that you can actually override these operators in Python and make use of them. And then this is exactly what the Python library Clifford is also doing. So it implements here the exterior product. And what it returns is a multivector. Wait, what's a multivector? What we have so far are k-blades, constructed as exterior product of k vectors. What one might want to do now is to just formally add k-blades together, because why not? I mean, addition is very natural to us humans. Why not just like if we have two blades A and B and we add them together, we write them next to each other and put a plus sign in between. So we have addition as permitted operation to construct new elements. So what could possibly go wrong? Well, let's consider R4 with the bases E1 to E4. And what might be a bit shocking at first is that we cannot write this blade E1 wedge E2 plus E3 wedge E4. We cannot write that as exterior product of just two vectors. So right now we have like this sum. We have on the left we have a blade, on the right hand side we have a blade, but we cannot write this as exterior product of two vectors. And to prove this, let's take any two blades A and B and write them as their linear combinations of basis vectors. And a wedge B, we denote it as the blade capital B. Now, if you expand the product of A wedge B, what you will find are these expressions. We actually have those two expressions coming up here. So E1 wedge E2 and E3 wedge E4. So we want that all other expressions are 0. Right? Because in the end, A wedge B should be like this big blade B. So all the other expressions here should be 0, and therefore we obtain these 4 expressions. Let's write A1 divided by A2 in a bit different way by just putting it 1 in between, like the A4 divided by A4, and then use the results we already obtained. So A1 divided by A4 is B1 divided by B4, and A4 divided by A2, that one we already have as well, but here the B4 cancels and we obtain B1 divided by B2. If you plug this expression into the first term, you will find that it should be 0. But well, if it's 0, then we don't have any E1 wedge E2 element. So by contradiction, we cannot write our blade B as the exterior product of two vectors. But then, you might say, well, if a blade is defined as an exterior product of k vector vectors, and B cannot be written as such a product, then, well, it shouldn't be a k-blade at all, right? We cannot decompose it. So blades are not closed under addition. Instead, what we call B is a 2 vector. And we denote it by changing the font a bit. So we're not using like the bold face B now, we're using the italic B. So that's a bummer. K-blades are not closed under addition, but nonetheless we obtain an object, so-called a k-vector, in a graded algebra. And in this graded algebra we have k-vectors, which are sums of k-blades. To get rid of any confusion, let's think this through again. So we have scalars. We started with scalars which are 0 blades. If we sum them up with a finite sum, we still have a scalar, like 5 plus 2 is 7. We still get a scalar. Then we had vectors, which are 1 blades. If we add together vectors, we still have vectors. Now with our new exterior product, we can do something like A wedge B. And what we get out of this is a 2 blade. This, in fact, we can also call a simple bivector, which we'll come to in a second. Now we can also have a 3 blade, as we've seen, which are simple trivectors. And in general, we can have k blades, which are simple k vectors. The new thing here is that if we sum 2 blades, we get a 2 vector. In this 2 vector, this we call bivector. If we sum 3 blades, we get a 3 vector, which we also call trivector. And in general, if we sum k blades, then we get a k vector. And here you don't have to stop. Formally, you can also define then what it means to add 2 vectors, 3 vectors, k vectors, vectors and scalars, and in general what you obtain is a multivector. So you can actually extend the exterior product to multivectors using its linearity and distributivity, and then you can write something like 1 plus E1. Here we have a scalar part and a vector part. And well, this looks a bit weird, like we're mixing elements of different grades, but this is what multivectors are. Just think of when you write a complex number, like 2 plus 3i, then you also mix together different stuff because you have 2 and then you have something multiplied by the complex number I. Think of it like this, you just add it together in a formal way by writing elements next to each other and putting a plus sign in between. The advantage of this is that we can unify different geometric operations in a single algebraic framework. And then we might even want to wedge this together with another multivector. So we have in general an exterior product even between multivectors. For example, think of this as using distributivity and then defining one wedge 1 as 1 and one wedge E2, well, this should be E2. E1 wedge 1 could be E1, and then we also have a bivector part that we cannot simplify any further. These k-vectors, they live here in this space that we've already seen when we've discussed k-blades, but now more general for k-vectors. If we add those vectors together, we end up in a new space, which is called the Grassmann algebra, or also exterior algebra. And the multivectors, they live here. And the difference in the notation is just that we drop this superscript k, because now we can have mixed grades together, as we've seen. Now, for example, the Grassmann algebra of the vector space R3 contains the following elements. We have scalars. We have the vector space with the bases E1, E2, and E3. We have a bivector space, like E1, wedge E2, and so on. And we even have a trivector space, like there's only one element here, E1, wedge E2, wedge E3. If you count the number of elements for each grade, then we obtain one scalar, 3 vectors, 3 bivectors, and 1 trivector. And maybe this sequence rings a bell. And yes, indeed, it's part of the Pascal triangle. So what you write here is the n, 0, 1, 2, 3, 4, 5, and the subspace grade k. And in our case, we chose n to be 3 because we considered R3. And we found these elements with different subspace grade. So with subspace grade 0, like the scalars, we found one element. With subspace grade 3, we also just found one element, namely the trivector. E1, wedge E2, wedge E3. And in general, as you know, in the Pascal triangle, the elements are calculated as the binomial coefficients, so n choose k. And so we can now write the dimensionality of our Grassmann algebra. So we have to sum up all of our basis elements. So we have to take the sum over k, where k goes from 0 to n, and then add together those expressions, so 1, 3, 3, 1, which come out of the binomial coefficient n choose k. And well, mathematically you can show that this is just 2 to the power of n. And in this case, let's verify. Well, we had R3, so n is 3, and 2 to the power of 3 is 8. And indeed we have 8 basis elements. And as you've seen beforehand, we can also write them a bit more compact. For example, the trivector, we can just write E1, 2, 3. Now with all of this, what if somebody gives you a multivector, but you're just interested in one part, like in one part with a specific grade? For this case, you can take the grade operator, where you put the element into brackets and you write k as a subscript. And then what you extract is like the multivector part of that grade k. For example, if you have this multivector A and you wanted to extract the bivector part, like the part with grade 2, then you could just put this into brackets and write a 2, and you would get this part. If you wanted the trivector part, you would just write a 3 and so on. Like for the 4 vector part, we don't have anything here. Likewise for the vector part, but we have a scalar part in this case with coefficient 5. Okay, now let's take a step back. We've seen the exterior product, even how it generalizes to multivectors, but what's it use actually? We've encoded into one product the span, the weight, and orientation. What can we actually do with it? Let's see an example from computer graphics. which is backface culling. So imagine you had a torus here, like a donut, and in computer graphics, oftentimes you mesh it into polygons in general, and oftentimes into just rectangles. But you can also use triangles, as I've done in this case. So now we have a wireframe representation of this torus. But it looks a bit crowded because we see so many faces. We see the front-facing faces, which have a counterclockwise orientation, and we see at the same time the back-facing triangles, which have a clockwise orientation. Now, when I say clockwise and counterclockwise, what I mean is this 3D object, obviously it has to be projected onto a 2D plane, otherwise you couldn't look at it on your screen right now. So although it lives in R3, it has to be projected into R2. And then in R2, we have those triangle faces where some of them are counterclockwise and some of them are clockwise in their orientation. What we can do is just remove the clockwise, so the back-facing faces, and obtain this really cool structure. As you see, this is only valid from one point of perspective. If we rotate it, then it doesn't make sense anymore. Just if we stay in this one position where we project it. Now, the code to write this animation was really easy. Think of the triangle spanned by 3 vertices, V1, V2, and V3. And we want to write a method that checks if this triangle is back-facing or not. And this triangle, it lives in R2 now because we've already projected it. Now with the exterior product, we can easily find out the orientation. So you just take the 2 vectors from the point V1 on. So we have V3 minus V1 as one vector and V2 minus V1 as the other one. And this is now our blade B. And we can just mirror exactly that into Python code. The library allows us to even write the exterior product as we've seen because it overloads the operator. And then what we want to do is retrieve the component, the bivector component, E12. The syntax for this in the library is just you write B and then in square brackets you write the expression you want to retrieve. So in this case, 12, like E12. And now we return whether this expression is smaller or equal than 0. Because if it is, then we say it's back-facing. If it were bigger, then it's front-facing. So this was really easy to write, and it allows us to think of a problem visually. But watch out, this is not to say that this is computationally more efficient. In fact, most of the time it isn't, because you have to implement this algebra and the dimensionality increases with 2 to the power of n. So yeah, in terms of efficiency, it's probably not the best, but in terms of how you think about a problem and how you can prototype it, it's really cool to see that you can use your visual understanding of a problem and play around with it directly in math. As another cool example, let's consider invertibility. And before we do so, let's just quickly talk about reshapeability of bivectors. So if you have the bivector A wedge B, and now you take another bivector where you just move this vector B along the line parallel to A, and where you get another area element, A wedge B prime. But in fact, it's not another area element. Because of the properties of our exterior product, we cannot even distinguish between those two. So A wedge B is the very same element as A wedge B prime. Think of it as kind of like an equivalence class. And this is not at all a disadvantage. So for example, what we can do now is make use of this fact to calculate the intersection point X of 2 lines L and M. To describe the line L, we have a vector P that brings us onto the line, and we have a vector U that tells us the direction of the line. Then for the line M, we have the same scenario, so in this case a vector Q that puts us on the line, and a vector V for the direction of the line. Now what we want to find is this vector, this orange vector X, that gets us to the intersection point. Think of this vector X as a composition of 2 vectors. One vector in the direction of U and the other one in the direction of V. And then this vector X would just be a linear combination of those. What we have is the bivector U wedge V. So this is this planar element. And if you think about it, then this area here is just Q wedge V. Because you take V on the one side and then As we've seen, we can reshape the area element if we just move the Q along the line parallel to V, which in this case is just the line M that we are considering. And this gives us Q wedge V. Now, in the context of geometric algebra, one can actually show that the exterior product is invertible. And what this allows us to do is write this expression, Q wedge V divided by U wedge V. And what does it tell us? Well, it's the factor by which we have to scale the planar element U wedge V to obtain the planar element Q wedge V. And I've color-coded it in orange already because this factor tells us the length of the orange vector indeed. And the same thing we can now do for the other side. So here the planar element P wedge U is this area. And then when we write P wedge U divided by V wedge U, we find out this factor by which we have to scale our small element to obtain a bigger one. And then with this in mind, we can write down algebraically what our intersection point is without thinking of any coordinates. And I think here you really see the power of this geometric framework where it allows us to think of algebraic entities in a visual way. You can even take this further to geometric models that we won't discuss here, but just to give you an outlook, what we just did all the time is we considered the vector space model in Rn. Here, vectors represent points, we have somewhat efficient computations, and the dot product, cross product, and rotations, they work naturally. But when we want to have translations, we cannot write those as geometric products, and we have no unified representation of all rigid transformations. This is overcome by the homogeneous models, where we add one dimension, which is a homogeneous coordinate, so it's kind of like a scale invariance. And then in this model, lines and planes, they represent actual geometric objects. And in this case, translations, they become rotations in the extended space where we added one dimension. But here we have the problem that we cannot represent angles and distances directly, and circles and spheres, they also have no natural representation. And then in the conformal model, if you even add one further dimension, which is also negative, it's just some outlook here, then we can represent circles and spheres as blades. Angles are preserved under conformal transformations, and we have a framework that unifies the treatment of points, lines, planes, circles, and spheres. So this is a really beautiful model that allows us to treat those elements just as like elements of our algebra, and we don't have to distinguish between them in our computations. Now, if you implement this naively, then of course it's more computationally expensive, and you also have some redundant representations. For example, points, they have an internal degree of freedom. So, well, yes, they also have disadvantages, but many advantages over what we've seen so far, which is the vector space model. So as a conclusion, I hope that I could give you a bit of an introduction to what the exterior product does. We've talked about subspaces, we've seen some properties of the exterior product, and we've seen how they actually make sense visually. We've then discussed what blades are. We also seen how to kind of do operator overloading in Python. Then we went over to adding blades to obtain in general k vectors, and then adding those k vectors to even obtain multivectors. And then we did some calculations with multivectors to get a bit of a feeling and intuition for them. And we've also seen two examples of how we can actually make use of them in code for computer graphics, here for the backface culling, and as an application of invertibility, we found out what the expression for the intersection of two lines is. And with that being said, Happy New Year 2026. I hope you're doing all fine. Have fun with math. See you next time. Bye.